this session is general formulas for the probabilities of association hypothesis in the probabilistic data association paper. So I'm going to state a result that I can derive as a theorem. This is the probability of the association event A given all my data. It's proportional to one of two possible options depending on whether we have a misdetection or detection. So in a misdetection case, show that this is proportional to 1 minus PE times the cardinality pointwise function evaluated at the number m, which is the number of measurements. So that was in the misdetection case. In the other case, it's going to be some likelihood thing, which we will define, check out n times PV times cardinality pointwise function, now evaluated n minus 1 measurements divided by m and the spatial capacity of the measurement ZA. So this is first case if A equals 0. The second one is if A is larger than 0, and then define this likelihood thing. So this is an integral. Then I have the likelihood of the measurements conditional on the target state. The part of the integral here is the solution of the target state. So also notice now that I'm dropping some of the subscripts k. Don't write a time index for the association events, and also for this number n, just to simplify notation a bit compared to how it is done in textbook. So this is what I'm going to derive. Then we are going to get mathematical proof of this. I guess I should also point out before we go into that this is a very general expression. I have not made any assumption of the form of these PDFs that enter this likelihood thing, which I also should have a superscript A on. This is the likelihood measurement number A. I've also made no assumptions of what this mu, the cluster cardinality distribution is. So, well, first of all, I need to relate the association events with information carried by the current measurement set. And so this is going to this is my starting point. So I start. Then I'm going to expand this a little bit before I do anything more. So what I've done here now is that I've taken out first the last measurement set, and then I also say that it carries really to this information, the measurement set itself, and also the cardinality, because the cardinality is part of this, but I can also use that as a separate piece of information. Once I've done that, I can use bias rule. So, while using bias, I have taken this is the likely part of bias. I just have to take this, which I equals data, on the left side of the conditioning bar. What I'm then left with is A, conditional n, and the previous measurements. But without using any further information about this current measurement set. This measurement set has nothing to say about what n A, how likely A is when once N has been conditioned. I know how many measurements I have. To say anything about how likely these measurements are, which after all are what is given by the posterior probabilities of A. I will need to look at the current measurement set. That's not part of my prior. So then I can forget about all information about the previous measurements as well. So then I need to look at what this thing is for the different possibilities of A and what this thing is for different possibilities of A. So basically I'm going to have to deal with 4 cases now. 2 of this, 2 of this. So A equal to 0 or A is larger than 0, not larger than 1, sorry. So we take them case by case. A equals 0. This likelihood, the current measurement set conditional on only N and the association event and the previous data does not include the state. And clearly what the state is very important for how likely the measurements are. So to do anything with this, we have to expand this by means of the total probability theorem over the state data. Meaning that I'm going to write this as an integral of C N A equals state and the previous. And then, of course, I also need then to include the area of the state. This is how the total probability theorem works. Then I'm going to integrate all that. So this is the same. This thing, I can do something with it because I know that now since all my measurements are from cluster, none of the measurements can be from the target if A is going to be equal to 0. That's the misdetection rate. So in that case, I know that all these measurements are independent of the target and also independent of the products. So what I get here is another, I guess I have again this integral. Then I have the spatial PDF. So the PDF translate. So I integrate over this, where I can take this product outside of the integral. I'm left with the integral over the prediction, which is equal to 1 because it's a PDF. So I'm left with just this product. That was quite simple. Let me continue with so that I need to do the likelihood for case A is bigger than 0. Just write it like this. Since A can be arbitrary. So again, I have the same, I have the same integral as over here, just with arbitrary A instead of A equal to 0. In this case, one of my measurements, the measurement indexed with the value of A, will depend on the target. All the other measurements will not depend on the target. So this is something I can write it like this. So here I have all the cluster measurements except the one indexed by A. Then I have the measurement, the likelihood of the measurement indexed by A. And of course I have the prediction again as part of this integral. So now I can just take this out of the integral, but this remains in the integral, and it's by definition then equal to the n A that I have defined over there. This is the same as NA equals A. And then I'm going to do like this. So I divide by the cluster density of that particular measurement. Because then I can write this product in a slightly simpler way. So instead of having skipping one measurement, now I just have to do all the measurements in this product. And then I guess statisticians would like to call this thing in a fraction for a likelihood ratio. So then I've dealt with all the likelihood information. What remains then are these probabilities, which we call the prior probabilities, the prior association probabilities. So first I do the prior probability for A equals 0. What is the prior misdetection probability? Now, to make it clear what's going on, I'm introducing a new notation. So I use this lowercase m for the number of measurements. This is really a random variable. So I guess I could have written this with a capital N, but that's not commonly done and will probably cause more confusion. So instead now I mark its realization by m with a bar on. So this is realization of n, and this is the actual, this is the random variable of n. So now I'm saying what is going to be the probability of misdetection given some particular realization of n. So having a misdetection means that all measurements must be from cluster. So this means that the number of false alarms, which I call phi, it's going to equal n bar, given that n equals n bar. Then I'm going to use bias rule on this. Then I get the probability of n equals n bar, conditional on phi equal n bar. The reason for this is that I would really like to condition on my knowledge about phi, because I have a model for the cluster. Encapsulated by this probability. What is the probability of phi being equal to n bar? And then, of course, I have the denominator, which doesn't concern us, but the right. So what is this? Well, given now that phi equals n bar and n equals n equals n bar, I just have a misdetection. So this is simply 1 minus the detection probability. This thing is the clutter cardinality distribution evaluated in bar. And then I have this denominator that I don't get. So then I have one more bioprobability now for the case that A equals something bigger than 0. A takes any of the measurements. So let's suppose if A equals some number I bigger than 0. Again, given M some particular realization. This is the same. This is basically an expansion. Sum over possibilities of what the clutter cardinality can attain. Now, this probability of having A anything less than 0, if this one is not equal to n bar minus 1, is going to be 0. So I only left with this term in my total probability expansion. So, given this information, that I have n bar minus 1 clutter measurements and n measurements, then A can attain any of those n measurements. So this was probability simply 1 divided by n. And then, my second, which is going to go a bit more. So then again, I'm going to use bias on that. Fraction. Given 5 minus 1. Is the probability that 5 equals the same denominator as I have here. So that's the same as the detection probability. That's the cardinality distribution from n bar minus 1. Divided by, and then okay. So then I have all the things that I'm going to combine together in order to arrive at this result, which I would like to get. It's just a matter of stitching it together to see if I can summarize what I have prepared. So I have the likelihood is now proportional to either 1 or n divided by the clutter distribution of measurement A. distribution value of M. Now I don't care about the difference between realizations and the actual value anymore. Or proportional to the probability of detection times the distribution of M minus 1. If A equals 0, A is greater than 0. And now the remains is just to put all of this together. You will see that this times this is obviously what we have up there, and this times this is what you have over there. So you're done.